Alright, we're going to look at some more things we can do to evaluate indefinite integrals here. In addition to properties that we've already seen, we can use trig identities, we can use algebra, all those things that we've learned in math that we've done in the past. This first integral here, we are looking at integral of that function there. Alright, to evaluate that, well, the simplest thing to do is just expand that algebraically, right? Make this, if we have x squared plus 1 squared, we get x to the 4th plus 2x squared plus 1 dx, right? Expand that and then integrate it term by term, right? So you got, it's going to be bumped up to x to the 5th, 1/5. You have, this is going to be x to the 3rd. We got to divide by 3, and then we had a 2 there to start with, all right? And the last one here is just x, and then we need a constant. Right, so that's that first one. Expand it. I'm going to go down here and do this thing right here. You have this expression here. You can take that and then divide it by what's on the bottom. Divide each term and write them separately. So you could say this is equal to integral of x squared over x to the 4th plus, except it's minus, 2x to the 4th over x to the 4th. Or in other words, if we write that, I don't have much room here, but integral of, I'm going to say x to the minus 2 minus 2 like that, dx. Now, I'm out of room here. I'm going to make it a bit more room by squishing this up a bit there. So we can say that this is going to be equal to, we've got to bump the power up 1 to minus 1, and we got to divide by negative 1, so let's put a minus in front, and this is going to be 2 times x plus a constant here. If we're going to write it in more like the form that we had there, can't squish this much more, but I'll try. If I squish that up, if you're writing in the form that you had there, it's going to be minus 1 over x minus 2x plus a constant. Right, that's what that is. We will go up here to this one. It's always a good strategy to try and write it as a power, a single power, and then you can use the power rule for integration. So x, this is like integral of x to the 1 times x to the 1/2 dx. So in other words, that is like x to the 3/2, 1.5, right? And if you're going to actually evaluate that integral, you got to bump this power up 1 to 5/2, and you got to divide by 5/2, which is like multiplying by 2/5 plus some constant. All right, so write it as a single power. And then last down here, looking at this, we can simplify this just by taking that and multiplying it through and then writing it as a couple powers there. So we can make this x plus x times that is going to be 1 over 2x to the 3rd, right? Or if we want to, let's just leave it like this for a second. X over 2x to the 4th dx. And again, writing this as a power here, x is like x to the 1, and this is like 1/2 x to the minus 3. And we've got the integral of that. So if we're trying to do this, look at them as powers like that. Then we can evaluate it here. X to the 1 is going to be 1/2 x squared. And this is going to be, bump this up 1 to negative 2. And we already have the 1/2 there, but we got to divide by negative 2, right? Got to divide by negative 2, so this is actually going to be 1 over 2, but times negative 2 on the bottom, plus a constant. So simpler way to write that is minus 1/4 here, right? Minus 1/4, and that's what you have. All right. Now we're going to turn to looking at some trig identities as well down below here. You can also use trig identities when you're working with integrals involving trig functions if they help simplify things. So this first thing here, first integral that we're going to evaluate, sine 2x over cos x. There's two different variables inside there. There's 2x and x. Simplest thing to do is to change that one. using that trig identity that says that sine 2x is 2 sine x cos x. Okay, so replace it with that, cos x. Oh, and look at that, that cancels out. So we're going to have integral of 2 sine x. I'm going to put the 2 out there. Integral of sine x is just minus cos x, so this is minus 2 cos x plus a constant. All right. Now, second one down here, we have integral of, you could write that as 1 over secant. Sometimes you put the dx on the top like that just to make things more compact, but that means the same thing as that. 1 over secant, simplest thing to do is make that integral of cosine dx. And its integral of cosine is sine x plus a constant. And this third one up here, integral of cos x over sine squared x. Well, this one's a little trickier because it's not obvious what to do here, but I'm going to write it as integral of cos x over sine x. Going to write it twice on the bottom, because then you can see that this is actually going to be something that is actually cotangent. And this, the other part of it here, this part right here, 1 over sine x is actually cosecant x. Now, that, yeah, hopefully you happen to recognize that this is the derivative of minus cosecant. So you evaluate that integral, it's minus cosecant. All right, just because of that derivative formula. Integral of cosecant is minus cotangent cosecant. So you turn it around, that's what you get. Now this last one here is a bit tricky because that's not one of the things that you recognize from those derivative formulas. But you can use trig identities again here. There's a trig identity that says 1 plus tan squared is equal to secant squared, one of those Pythagorean identities. So we can throw the 1 over there, and tan squared is equal to sec squared minus 1. So we can make this integral of secant squared x minus 1 dx. So you're doing the integral of that. Secant squared is the derivative of tangent, and 1 is the derivative of x plus some constant. You got 3 terms in your answer there only because you replaced this thing that had 1 term with something that has 2 terms, and then when you evaluate the integral, that's what you get. All right, so there is using algebraic skills and trig identities to simplify the integrand before you start evaluating it. Change this a little bit, simplify it, or change it before you integrate it. There you go.